Okay, this is Bob Youngs, member of the TI team, now speaking as a proponent expert to just summarize the Chiou and Young's 2013 NGA West 2 model and answer the questions that are on the screen here, which are sort of interspersed out through the presentation. Basically, our model, again, as all the other ones are developed based on the peer NGA West 2 database, when basically we use the same criteria as before to develop acceptable events in terms of removal of events not considered shallow crustal and types of sites. One difference is that we concentrated, at least in the initial development and in the final assessment of standard error or aleatory variability, using data with recording from earthquakes with recordings of at least five earthquake recordings per earthquake in terms of the estimation. And we only used class 1 events, or what used to be called main shocks in our model. We did not even look at trying to develop a model for aftershocks in this round. The question 1 are basic changes in the conceptual model and approaches. The basic magnitude and distance scaling remain unchanged from our 2008 model. One of the major differences which everyone found, or most everyone who I think evaluated this, was the expanded database showed regional differences. In 2008, active tectonic regions were the same. Everyone modeled them all as being basically the same across the globe, but now when we get more data from all these regions, we see there are differences that we need to address, and we have addressed those in our model. We did see, in adding a lot of data from small magnitudes, some differences in the scaling with depth and style of faulting and dip at small magnitudes compared to large magnitudes, so we introduced some differences in that scaling into our updated model. In our previous model, we used empirical data to constrain the hanging wall effect, and the expanded database did not really add much to that empirical data, so we relied, in our case, on the simulation data to define the hanging wall model, and we probably relied on it more than any other team in the fact that our amplitude is based on the simulations, not only just the shape of it. And we've incorporated directivity estimates into the model such that we attempted to make our model centered on average directivity for earthquakes, so that the model would represent, the ground motion predicted by the median model would represent the average directivity effect for a random site around the fault, such that you would add directivity effects explicitly on top of it. So the model, we believe, is reasonably centered on an average directivity effect. This is just an illustration of our magnitude scaling, which remains basically unchanged. We transition from a scaling at high magnitude that's basically proportional to acceleration to at low magnitude to a scaling that's proportional to displacement. And we have a smooth transition between those two magnitude ranges, and that transition is period dependent. And we developed this in 2008, and Brian in 2010 showed that they work well for small magnitude data, and so we've retained that form for our update. That's requiring some adjustments to the parameters to make it work with the data set. Distance scaling, again, is unchanged. We do not have a magnitude-dependent geometric spreading. We have a nearest source additive distance term in this distance range, and then we transition at about 50 kilometers. We transition from sort of body wave spreading to surface wave or LG wave spreading with a slope of 0.5, and we do that as a smooth transition with this form rather than an abrupt transition. And then we have a far field anelastic attenuation term to represent the decay at large distances, and this term is magnitude and frequency dependent. So that form was in 2008, and it remains the form we're using today with, adjustments to the coefficients. Important changes were regionalization. We've identified regionalization in the large distance attenuation. in linear VS30 scaling at low amplitudes, and with scaling with depth to 1 kilometer a second. So those terms are carried to some extent through as much as we can through our model. The focus for our model was on developing a model primarily for use in California, so we concentrated on using California data, but we needed data from other regions at large magnitudes to refine the magnitude scaling at large magnitudes and to make perhaps a better estimates of aleatory variability. And one of the first important steps in our approach was we started off in the final model development by doing a event-by-event fit to every earthquake in the database that would allow us to do an event-by-event fit such that we can establish the form of the variation of the inelastic attenuation with magnitude and period. It helped us define the regionalization and to variation to refine the evaluation of this near source additive term, which affects basically it affects for the finite fault rupture with the expanded database. And also importantly, it establishes the distance-specific truncations for how far out we're going to use data from each earthquake. Because we have the problem in all of these data sets are with the horizontal truncation of the data at low amplitude as you move further away from the source. And it's, has been described, I mean, Norm and in their group, they evaluated this based on time, and clearly you can see a time migration of that as we go to better instrumentation. We can get more and more data. But we evaluated it specifically by event. So we did truncated, as a part of this analysis up here with the individual fits, we did those with truncated regression, and from that we estimated how far out could you use the data with a normal regression and establish basically get the same kind of fit. So we basically have an event-specific truncation for each earthquake. This is an example of the results of fitting the inelastic attenuation term as a function of period and of magnitude. And the solid lines are the fit to the California data, and they show, in our previous model, we assumed that the variation with variation with magnitude was period independent. It was basically the same shape at all periods, but clearly the data show that that's not the case, that the variation with magnitude of gamma, the inelastic attenuation term, varies between periods. So we allow that variation to occur in our assessment. So this is basically plots of versus magnitude of the inelastic attenuation term fit. This is the fit here is to a bunch of other data not shown on this plot, is to all the data from California, and then we've shown the data from the other regions by color on here, indicating that the data from China sit above it, which basically indicates that China is a different region. The data from Japan and Italy sit below it. They have a stronger inelastic attenuation, so we regionalized Japan and Italy together, and that New Zealand and Taiwan sort of fluctuate around the California model, so we placed New Zealand and Taiwan into the California set. So basically we have 3 regions. Some other modifications, style of faulting, which much weaker for smaller magnitudes. Something that Josef and Ken noticed was the effective dip, which we looked at and also found a strong effective dip, but primarily at small magnitudes. And that the depth to top of rupture scaling was stronger for small magnitudes, something that Norman mentioned earlier. So we developed, in our model, we basically do transitions between events around 4.5 and lower versus events above 5.5. We transitioned the scaling of those terms between those two. And then we centered the depth to top of rupture scaling on magnitude and style of faulting specific values rather than working off an arbitrary value that we used before of 4 kilometers. The hanging wall model, updated model, and the NGA West database is still limited to recording. Jennifer spent a lot of time looking at what data was added, and there wasn't much. So we utilized the simulation results. of the reverse faulting earthquakes which were conducted to evaluate that. The way we did it was we fit the individual simulation, each individual simulation set, each particular magnitude by an event-specific event-specific regression, and then we looked at the residuals from that, and we fit those residuals to develop a hanging wall model with a relatively simple form. And then we utilized that model directly in our analysis without modification for sites that were on the hanging wall, basically JB distance of 0. And then we utilized the decay off of that based on what we developed in 2008. So this is just a plot of a lot of data that show up in Jennifer's and Norm's, but plotted in a different way. These are residuals for individual residuals for a fit to the data, to the footwall data for a particular event, and these are the hanging wall site residuals. And we fit them with a very simple form that basically says that the amplitude of the hanging wall effect increases as Rx increases until you get to the edge of the rupture. So that's basically the magnitude effect comes in through the effect that larger events have a wider zone over the hanging wall so they can reach a higher amplitude increase. We did notice, which has been mentioned at least at the time, that the magnitude 6 simulations produce rather strange results compared to the rest of them. And noticeably, they peak very quickly and then decay before you get to the edge, whereas all the other data basically show an increase as you move to the back edge. So for this model, we assumed that there was some problem that we didn't understand, so we ignored those simulations for 6 in fitting the model. And this just shows that these panels show the effect of dip from 30 to whatever this one is down here. The fact that you can see a decreasing in dip. So we basically put in a cosine dip term. We use cosine dip because of the fact that arguing that the hanging wall is maybe primarily geometric and the width of the top of the rupture is directly proportional to cosine dip of the dip. And then this is just an effect to deal with. This is basically the form of the shape on top of the hanging wall. And then we have a decay term off of the hanging wall, which we developed before, with a slight modification. It's basically a function of RJB and the depth to top of rupture and proportion to the rupture distance. And this is a plot of the intra-event residuals from our data set fit with a model where the hanging wall term is fixed based on the simulations. And this is a plot of the empirical data. And this, so there's the 0 line is here. The locally weighted least squares fit to the residuals is a solid and its uncertainty. So we feel that using the simulation data is capturing what we see in the empirical data well. And that the trend of the decay of this term as you move away from on top of the hanging wall is fit well by this form. So the question 3 was, what is your uncertainty in the hanging wall factor? So we use the simulations directly, so there's a lot of data in the simulation, so that even though there's tremendous scatter as shown in the individual simulations, the model has very low uncertainty because of the tremendous amount of data fit, but that isn't really the uncertainty, it's just the uncertainty in our fit to those simulation data. A comparison of the predictions from our fit to those simulations compared to Jennifer's model may give us some indication of what the uncertainty in the hanging wall factor is. If you look at the uncertainty in the median prediction here, in other words, how this is a 90% confidence interval on the median prediction of those residuals, that would suggest uncertainty on the order of like 0.13 log units. So that's some indication of a level of uncertainty in what the hanging wall factor might be from the empirical data. Our scaling to small magnitudes and deeper depths was basically based on extrapolation of the form that we chose to, so it was not based on any thing magical. The style of faulting effect is just captured in this term, and it just decays as you go deeper. It just causes the hanging wall factor to decrease. And the magnitude term just comes in through the effect of the narrower width on the hanging wall, so we don't let the hanging wall term ever go to 0, It just gets very close to zero for earthquakes that are so small they have very little width above them. So it's purely an extrapolation of a model that's sort of fit to large magnitudes. Site response model update. We did, as I indicated before, developed regional models for low amplitude motion scaling with VS30, California versus another region versus Japan. We retained our nonlinear model developed in 2008 based on analysis of the empirical data. And then we did develop regional differences in Z1.0 scaling between Japan and California. And based that on centering the scaling on region estimates of Z1.0 as a function of VS30 so that the model could sort of be applied. So the model is now centered on the average Z1.0 for a given VS30 so that you don't necessarily have to go estimate Z1.0 in any region. You just plug in 0 for the change from the delta from the average value, which is what you would know anywhere you didn't have a Z1.0. And again, I indicated we've incorporated directivity through the direct point parameterization of directivity based on Chiou and Spudich 2013. Brian computed the values of this term and then computed the average value of sites around each earthquake and developed a delta DPP for each recording, and that became a regression parameter such that the model now is centered on the average directivity for each earthquake. Question 2 was estimate the uncertainty of normal faulting factor. Because of our process of selection, we ended up with very few normal faulting events. And so we decided late in the game that we basically didn't have enough data to really evaluate normal faulting, and we hadn't concentrated on looking at normal faulting. So we went back to our 2008 normal faulting factor and just plugged it in unchanged. The data set that when we did do regression, including normal faulting factor, we actually got stronger normal faulting effects than we had in 2008, but not a lot of data to evaluate that. But one indication is from the analysis that Linda and I did as a part of epistemic uncertainty and looking at how well the models are constrained. Then on average, the uncertainty in the median for normal faulting sites are from the regression fits that people are doing is about 50% higher than the uncertainty in strike slip and reverse events. So that would be at least some indication that we should have an uncertainty in the median for normal faulting that's something along the order of 50% larger than for strike slip and reverse. Question 4, uncertainty in estimates at magnitude 8 and 5, and here I will just point to the analysis that Linda and I have done for uncertainty, and these are figures out of that plot. It's indicating these are the uncertainty as a function of distance. These are sort of the average uncertainty in a ground motion prediction or ground motion model across the 5 NGAs as a function of magnitude and distance. And you can see for magnitudes below about 7, they're all well centered, but as you get to larger magnitudes, the uncertainty goes up so that the uncertainty in the median should be, again, about 50% higher for magnitude 8 than it would be at a magnitude 7. So that would be one way to look at what that number should be. And what is the uncertainty in the standard deviation? So this plot shows the way that we estimated the variance terms. So we basically, once we've done the mixed effects regression, we have a whole set of total residuals. Then we use maximum likelihood estimation of the parameters of tau and phi of that set. And basically looking at that, we evaluated that we have magnitude dependence still in the data set. And we estimate tau and phi at magnitude 5. And we do not include the data below magnitude 5 in that because we see a big step upward in the estimate of phi at below 5, which is maybe coming from the mixing in different kinds of metadata. But there's a clear step up in phi as you cross from above 5 down to below 5. And so tau 1 and phi 1 are the estimates at magnitude 5, and tau 2 and phi 2 are the estimates at magnitude 6.5 and larger. And the vertical lines here are the 90% confidence intervals on the estimates of tau and phi from that maximum likelihood solution. So we can, it indicates that the uncertainty in tau is about, say, 0.08 or so for magnitude 5, and about 0.05 or so from here. We can certainly give these values in terms of their estimates, what they are. The uncertainty in phi is, of course, much tighter because it uses a lot more information to gain it. And you can see the bump. The bump is there in, I think if anyone looked at the residuals there, it's in tau. And I'll go into some discussion about it in a minute. But what we did was we fit a smooth model to this, basically trying to capture this variation with period, and stay within the uncertainty estimates of the parameters, but not introduce a sharp bump in tau, which will basically affect the shape of estimated hazard at low frequencies, and produce some perhaps unusual looking response spectra. So we chose to smooth through it basically within the uncertainty estimates that we had of the parameters. I think I have all of those taken care of. And then the next question was, what was our basis for smoothing through the peak in tau? So there was some speculation in some of our working meetings that this bump might be somehow interaction between the band of the motions that Dave mentioned, or maybe kappa was already mentioned. So I actually did the experiment that Dave was talking about. So I took, this is a simulation with a simple point source stochastic model for a magnitude 6.5 at 30 kilometers, which is where we know everything as well as we know anything, we know that, for a rock site. So I simulated a bunch of earthquakes using a median, I can't remember what the median parameter, doesn't really matter that much, but used the sigma and stress drop of 0.3, so each event has its own event-specific stress drop. I simulated kappa at the sites, so every site that's for each earthquake, it's a sampled kappa out of a distribution with a standard deviation of 0.3 natural log units, which is some magic number that Walt has been using off and on over time for the uncertainty in kappa. And I also put in an uncertainty in the standard Western US AMP function of 0.4 natural log units, basically to address our variability in site amplification from site to site. So if you do that simulation, and then you take all those residuals and you fit them with random effects, you see basically a bump in phi and no bump in tau. So this is the variation of tau with period. As you get to low frequency, of course, it goes away because it's all, in this case, it's all stress drop. It's the only thing affecting the event. They all have the same moment magnitude, so this should go away. And phi is showing up in here as kappa is affecting this as it's rolling off the high frequency portion. So it shows up in phi, but does not show up in tau. So then the question is, how can we get it into tau? So one way to do that is to assume that there is a correlation in kappa per event. In other words, each earthquake is occurring at a specific location. It's sampling a different group of sites, and the average kappa for each earthquake will not be at a global average. It will vary from earthquake to earthquake. So if you introduce a correlation in kappa with the events, so we sample, now when I select an earthquake, I grab a stress drop, and then I simulate an average kappa for the sites recording that earthquake. And I basically, for this example, I took half the total variance and put half that variance on the event-specific kappa, and then the rest of the sites within that are distributed about that event-specific kappa with the rest of the variance, such that there is now a correlation in the average kappa per event. If you do that, you can pull that bump into into tau. So it's a possibility that this bump in tau is coming from some correlation in the average site effects the site conditions among the events. That's one speculative answer.
You don't. Kappa is the only thing that's creating that bump, right? So if you took kappa variability out and just had the other two, you probably wouldn't see it at all.
I wouldn't see it.
Because the site amplification isn't doing
That's
it.
basically the site. I moved the whole amp function up and down by the same factor.
Make a bump.
So it's coming from, in this case, it's coming from kappa. From a correlation from basically event-specific kappas, average kappas in this simulation. We did also look at the California data, and this is a similar plot to the one that Dave did. This is showing tau and phi for California data above magnitude 5.5. This fits to the residuals. And what's shown on here are three analyses. One is just Northern California, which are shown by the red. And the blue is Southern California. I have the colors backwards the way they should be in terms of the political map. And then the green is a mixture of them both together. And you can see that especially for Northern California, there's no bump in tau. There is a suggestion of a small bump in phi. If you look at Southern California, there is no bump in phi at all, but there's maybe a little bit of a bump in tau. And if you mix California north and south, you get a little more of a bump in tau. So our conclusion is that the bump may be an artifact of event variation in average kappa or average site conditions that are affecting the frequency of that. And we smooth through the bump within the uncertainty values of the estimates of tau, basically to not introduce an artifact into our response spectrum. And one thought that occurred to me while we were sitting here is that if we are going to include some kind of this effect in our GMPE that we're developing for this project, the question is, where should this bump be? At what frequency? Because this data is soil data. We're analyzing all of tau and phi is coming from soil data. And should we be moving that, if we're looking at rock site estimates, should we be moving that bump to a higher frequency? It's just a speculation. So, any questions? TI team first.
I found these results very interesting, and particularly the difference between Northern and Southern California. And I'm wondering now, based on the last couple of presentations, and I don't know the feasibility of doing this, but if it would make sense to maybe do some sort of bootstrap sampling of the data set to see if there's maybe a smaller subset of observations that could be leading to the bump.
It's possible. I think there is one thing about it's difficult to bootstrap out of a random effects hierarchical system. Because if you had balanced data where every earthquake had the same number of recordings, you could do it. But the fact that the sample size for each earthquake varies tremendously, so there are issues with bootstrapping out of that kind of distribution. I mean, people have tried to do it, but I've looked at papers, and seen how to do it, and they basically sort of say, well, we did it, but we're not saying this is the best way to do it or the greatest way. So there is some difficulty in bootstrapping, but it's certainly something to you could try. I think Ralph was next.
So, my question has to do with the Z, the Z top of rupture, because you have a strong dependence on this, or at least that's if I understood it correctly. Whereas both Dave and Youssef had said that they don't have any dependence now on the top of rupture in their Is that true?
Well, I will.
Or did
I will answer
misunderstand?
my understanding, and then they can correct me. So Dave, BSSA does not. Joseph and Ken use hypocentral depth instead of top of rupture.
So
And they correlate hypocentral depth. There is a correlation between hypocentral depth and top of rupture.
Okay.
But they chose to use hypocentral depth as the parameter, as the predictor parameter, because they got a better correlation with it. And when we, actually in 2008, when we did our first analysis, we found that hypocentral depth actually gave a stronger correlation than top of rupture. But because I was doing hazard, I said I don't want to randomize over hypocentral depth. I'm going to use top of rupture.
But the hypocentral depth is certainly, you know, a well-known physical parameter that is always going to be specified by the seismologist who locates that particular
Well, I don't know about
earthquake.
the well-known part, but yes.
Yeah. Well, let's put it this way: it has to be known if you're going to specify the earthquake. How well known it's, you know, how accurate it is another
Yeah.
question. But top of rupture is got to be much more variable in the analysis than the hypocentral depth. Would you think?
In the analysis,
I mean, when anybody puts in a top of rupture for a particular event, that's not well known. I mean, it's taken from kinematic models, it's taken from other things, but it's not a parameter that comes out of.
But surface rupturing faults are really clear, right?
They're
So
clear.
there's
At
some
zero,
that we know zero's better than we know a hypocentral depth may be there. But you're right. Bob talked about hazard, and I think it's important that there's a penalty for using hypocentral depth, and that is in the future earthquake calculation. Now you need a distribution of that as well. So it's an additional parameter that we would have to then randomize, and that may blur the benefits of the improvement in the model.
I was just removing the loops.
Yeah.
Tom, I think? I'm surprised. Tom has a question.
So have you at all looked into using downhole data to answer the question whether or not this bump might be a side effect? There's lots of it from Japan, of course.
Downhole.
Yeah.
Adrian might be able to, have you looked at Tao's downhole to see if it's any different, Adrian?
I mean, at 10 hertz, we're only looking at the upper couple of meters, right?
There are differences.
It's not.
There are differences in downhole standard deviations, but I have not looked at the shape, or I don't recall what the shape is. So.
I think we're good.
If your concept that the bump is due to kappa, which I think makes sense, at least that's a good
First arm wave.
a good candidate for this problem. Kappa is where you put all your high frequency problems. Shouldn't we be able to do finer regionalization and then figure that out?
Well, that or site or you know, yes, a single station. I don't know. It might be able to look at that to try to see if we can pull it out from that. I mean, as this is finer regionalization of this is regionalization of California,
So let me,
which is
Linda, are you going to cover, when you do single station signals for California, are you going to be able to show us that there's a bump in Tau? Did you even look at Taus at all? Okay.
I expect. I mean, this is the data that, I mean, Dave looked at it also. I don't know what the small magnitudes show. Small magnitudes don't show as strong a bump as the large magnitudes do in terms of Tau. And in California, you know, there's not much of one. at least above 5.5, but I don't know what the smallest stuff is going to look
But
like.
your fundamental assumption here is we've got a correlation in the data set that's mapping the side effect
It might be,
into tau.
our assumption is that that's the side effect perhaps being mapped into tau because of the fact that we're sampling only a finite set of sites for each earthquake. And I can introduce a bump in tau by that process. Whether that's the right explanation, I don't know. But it's not, at least if you have a model which says that you have a variability in stress drop that's affecting your event terms, that shouldn't show up as a bump in tau from the stochastic point source simulation. And maybe there's some other phenomenon that might be doing that, but it's not an interaction of stress drop and kappa. Joseph, I think, was first.
We see the bump in small magnitude also, but it's shifted towards shorter periods. So it's 0.07 seconds, something like that. But it's in a small magnitude as well as large magnitude.
Yeah, I don't have a plot of tau for events below 5, so it might, I mean, that would be, I looked at. Adrian.
I just checked our sigmas for surface and from borehole, and the borehole is much flatter. You see a small bump, but not at 0.1, at actually lower frequencies, but it's very small, but generally very flat for borehole. But this is total sigma. I didn't separate it. I don't have the plot here.
You have to use it.
Christine Goulet. So I've done similar thing, and I'm looking at it, and I've done it, and that bump is showed in phi, not in tau. We're using the KickNet data.
So the borehole data, is that right, Christine? The
Let me
downhole?
look at my phi amp.
Okay.
I'll get back to you.
Oh, I just want to reiterate what Yusef said, that we do find a definite, very strong bump in tau for the small magnitudes, and it's more like 0.6. It's shifted to shorter periods for sure. 0.06. Thank you.
That would still
So
be
it's-
consistent with kappa, though, right? Kappa would do that to you still, because you got the richer high frequency content, I think.
So that is seen, just to confirm, so in my phi amp, so it's when you compute the phi of the amplification itself. So it's then seen at this, it's really the phi of the amplification. Around 0.07 or so, 0.06, so smaller. Smaller than 0.1.
Christine, you're suggesting this is really a phi term that is getting mapped into tau based on
Yeah.
our correlation.
So
Is that right?
yes, that's what it looks like. And it's seen in the phi amp, but I guess it could be also combined with kappa. But I really see it in the phi amp, but which is then combining.
See, part of the reason this is that this separation, if we're just putting everything back together, you could say, well, does it matter where we put it? You know, as long as we have it there. But once we're going to single station sigma, if it belongs in phi, then
Yep.
we should take it out, and it shouldn't be in the tau term that we add back in there. That's going to be the consistency problem we have to deal with.
Yep.
So no, in summary,
In-
in summary, I think it needs a little bit digging into this issue.
So list for me what you want to see dug into exactly.
Is it really tau, as we just discussed? Is it kappa, phi coming to tau? So you have to dig into this.
Yeah, but I'm trying to write something, so I got to write a few specific sentences here, and I can't
Pierre,
just say.
Pierre will develop a scope.
So this is John Stewart. Are we pretty certain that there is no connection between stress drop and the bump then? I mean, you've basically concluded that it's kappa. Did you run simulations, for example, where you didn't vary kappa, didn't vary the site, and you only varied stress drop?
Yes, and it's flat. The phi is, I mean, tau is flat. If kappa is constant for all sites of 04 or whatever you want to pick, I did a bunch of them, it's flat. Tau is flat. So stress drop is only going to move, it's going to move everything up, and kappa will chop off the section, but it's not, I mean, maybe down to small magnitudes, but at magnitude 6.5, where we're seeing this strong bump, then the shape of tau looks like this. Tau is going, I mean, it's sampling back too far, so kappa should be up in here, but the corner is back over here somewhere. So it's not, when I did simulations with just stress drop variation for a constant kappa, I saw no bump. I saw changes, I mean, I didn't see any bump in like this.
Dave, it's hard to make a bump with stress drop.
Yeah,
You could
it's hard to make a
broaden it
bump.
out.
I can see what you're saying. I still reserve the right to redo that simple
course.
experiment, but I would certainly expect to have the delta 7 is clearly going to have more effect at the shorter periods than the longer periods, that's for sure. But I see what you're saying in terms of the bump itself. It's just that this business, what I was saying before, that when you go to very, very short periods, the PSA is being controlled by intermediate periods, you know, the ground
Yes.
motions, because
Right.
the true high frequencies have disappeared.
But
And
it's not
that's-
going to produce a bump there. It's going to just drag everything up and down.
I would think that
It would just, so at 100 hertz, kappa of 04 is this, the spectra as the stress drop goes up is being drug up by the motions back here. But it's all being pulled up.
I would have thought that the very short periods, that what you're getting would be very similar to what you got between, say, 1 and 0.1, something like that.
You mean this shape?
Yeah, that because
It would-
the actual ground motion frequencies that are controlling the PGAs are in there.
Right, but they're all moving with stress drop, right? So they're moving, therefore they're dragging the high frequency up and down with them. So
Yeah, and I guess this
they
actually
would-
comes into the magnitude
So
dependence.
the fact that we're looking at response spectra and not Fourier spectra,
I know, and that's,
that we're not,
that
I
was the
don't
basis
see, I
of what I
don't
was trying to
think
say.
that it will introduce a bump in tau.
Yeah. Okay, well,
Everything gets, I mean.
time will tell.
Yes.